Hello, everyone. Yeah, thank you all for keeping with us here. So we talked a bit before about already about training, and there is obviously a lot of things that we can say about training a neural network. This has been a subject of research for at least 40 years now. However, there are a couple of effective ways already to be able to use deep learning to train neural networks without having to invest too much. And really, what do we mean by investing too much? You can either spend a lot of time with a big computational budget, but usually what we found is that the budget in terms of engineers' hours is really the bottleneck here. Like how many people can you put on the problem, and how much are you willing to have them spend trying to optimize the neural network? And this is why trying to maximize so in order to maximize the effectiveness of people, there are a number of ways that you can use, such as a hyperparameter tuning. So essentially, in this case, what you can do is you can start from so you have a couple of networks that you would like to try, and you have a number of parameters that you would like to explore. You have for example, a number of learning rates that you want to explore in different start points if you want to test the robustness of your training methods, a number of different architectures, and so on. And Spark is really effective at managing the computation for you, because it can take care of loading the data, scheduling different tasks on a large cluster, and then collecting back the result after that, or writing them in a distributed fashion. So let's see a bit more how we can use Spark in that respect. So to come back to our MLlib components here, we have both estimators and evaluators. So how do we use them? So as Sven was describing before, when you have an estimator, this will produce a model and it needs to be fit. And this is where really you have all the learning algorithms and where you put the different choices for neural network architectures. And when you fit them, then you pass a training data frame, and then you have to specify a set of parameters. And this will produce one best model out of all the parameters that you give it, or a collection of all the models with all the results. And how do we get to know which one is a good model, which one is a bad model? So Spark and MLlib have already a big collection of evaluators. So evaluators let you evaluate how good your model is going to be against some held out data. And there are a number of these available. Probably the easiest to start with, if you have a binary classification problem, is the one-name binary classification evaluator. But you have a lot of other ones which implement most of the standard use cases you might think of, and they are modeled after what you can find in scikit-learn as well. So if you're familiar with how evaluators work in scikit-learn, then you can use that directly within MLlib pipelines and directly incorporate your deep learning components inside the MLlib here. So how does it work? So we start from an estimator for which we provide a map of parameters. And inside this parameter, so we want to build a set of parameters that we're going to try out for running training session. And then Spark will take care of distributing these parameters along with the model and the data, and then return to you the best model given that corresponds to one of these parameters. So in Spark, actually, it's pretty easy to express using so here in Python using the MLlib Pipelines API. So there's this param grid builder, which, by the way, is not specific to deep learning. It comes built in with Spark and MLlib. And all you need to do is to add a number of these parameters to this grid. And Spark behind the scene will build all the Cartesian product of all the elements. Someone managed to come in. I didn't. And then it will send it to Spark. So why is it how is it useful? So if you have an estimator, if you have an evaluator, then you can ask Spark to parallelize all the operations to find the best one. And Spark can take care for you of splitting the data into the training part and the held out part to evaluate how good the model is going to be, and then return to you the best model. So this is a very standard procedure in machine learning called cross-validation, and it is already implemented in Spark within MLlib. So the beauty of using MLlib pipelines in that context is that even if you have a very complex deep learning training stage at some point, you can incorporate it inside the larger pipeline, and cross-validators themselves correspond to estimators. So they will take care of finding for you within a more complex pipeline. They'll take care of finding the best model given a set of data that you probably transformed before and you already estimated before, and then it will return the model that you can use in subsequent transformers. So there are a couple of, so the deep learning pipelines has a number of these estimators available. As we were mentioning before, one of them corresponds to doing, to build a pipeline through transfer learning. The other one is built also on Keras, which I will talk more about later. So let's talk a bit about transfer learning first. So as a standard procedure, for example, you want typically in a pipeline to estimate some parameters, some of the best training parameters for each of your stages. And for example, here we can try different architectures, and we can try after that. We could try different classification on top of what we have for doing transfer learning. And so how can we express that in Spark? So all you need to do is express this pipeline using the MLlib Pipeline API to say that you're going to start with a featureizer, for which you don't know exactly how it is going to be built yet. Then we're going to plug logistic regression. So this one we're not going to change for now, but we could in a more realistic scenario. And then all we need to do is to express a grid of parameters that is going to be swept. And here we're, for example, just going to manipulate different architectures and then pass that to the cross-validator. So you see here how you can directly plug all sorts of architectures. So here these ones are predefined, but you can also add your own if you want to. And behind the scenes, Spark will take care of loading these architectures, distributing them, and making sure that it will give you finally the one that works the best, given all the other training parameters that you are going to provide as well. So this is if you want to. So this works well if you know already if you have some if you want to use some existing architectures, and so that works well if you have a predefined problem. For example, here you know you're going to work on images, and you have a sense of how they're going, how these neural network architectures are going to behave. But usually, you want to go beyond that. You want to build your own neural network. So it is pretty hard to do if you want to do it by yourself. And this is why people, instead of writing directly some Caffe or TensorFlow code, tend to use now some high-level wrappers for expressing these neural networks. So one of the most popular one is probably the Keras library written by François Chollet, who works at Google now. And in essence, it is a way to express all these layers that we talked about for doing neural network using a declarative API. And so it can also handle more complex cases. But the important part here is that it is pretty high level. It doesn't depend on the underlying framework. And then you can plug different deep learning libraries under the hood to run the computations. So for example, here I described a very small neural network in which essentially we just have one layer, one fully connected dense layer, then followed by an activation function. So all this API is available in Python, and we can reuse this description of neural networks and distribute the computations using Spark. So we have so deep learning pipelines incorporate this Keras estimator, which allows you to take a description of these networks and also all the parameters you need for training this network. So this is all single machine training system. But then we can use it. But usually we are not sure about what kind of parameters or what kind even of architecture we want to use. And we need, in order to find some of these good parameters, we need to try out a number of configuration. And this is what the Keras estimator allows you to do. So in that case, you can specify. So you start by specifying a model that you can save. So this is why it's called the Keras image file estimator. And then you can specify a number of fitting parameters. So here, for example, the batch size, which is a crucial parameter, is set. We just set one value, but you can add more. Actually, you can make a list and try out a number of other parameters, and it will return to you the best model it could train using the cluster under the hood. So if you want to, so if you do that, you can also use you can also specify a number of different loss functions, and you can try out a number of these parameters, and Spark will take care of distributing the data and of distributing the computations. So of course, after that, how do you know which one is going to work best? Again, we come back to a friend, the cross-validator, which is going to run all these Keras sessions in parallel, and then it is going to give you, based on the data set that it held out for doing validation, it is going to return to you the most, the best model out of all of these. So now let's talk a bit about how we can evaluate models. Usually for evaluating models, the easiest for that is to use something like one of the Spark methods. And Spark already incorporates a number of elements to check the goodness of fits of your model. So there's not much to add in that respect. But after that, we can, once we have selected the good models in our frameworks, we need to be able to apply this model. And usually, there's a number of ways that we can apply it.
All right, so we've trained the model, which is hopefully great, and we're going to apply it on some new data. Deep learning pipelines provides a couple of ways to do this. One is batch prediction, and another is to actually ship it as a Spark SQL. So we'll talk about these both. Let's look at batch prediction. So batch prediction is something that Spark is great at handling, right? You have a huge data frame of data. It should be able to apply whatever computation it is very quickly in a distributed manner. And we've wrapped that sort of computation as an MLlib transformer. We talked about transformers a couple of times. And we call that a model is a transformer in MLlib, so this makes a lot of sense. So essentially, doing any sort of prediction, deep learning or not, looks essentially like this. You create a predictor, which could be an object you instantiate, or it could come from an estimator.fit. And then you call transform on the test data to get the predictions. So there's actually a whole hierarchy of deep learning transformers that exist in deep learning pipelines, mostly for images. We talked about deep image featureizer and the predictor earlier. They're really transformers that take the data and either output labels or the representation, the embedding representations, right? They're powered by a bunch of transformers. This is like sort of implementation detail, but some of these are actually useful in real life. And they all take as input images and output an MLlib vector, but they take slightly different inputs as computation, like to define the computation. So, for example, this named image transformer takes in a model name, and it's going to load a pre-trained model corresponding to that model name, and then do something with it. We'll see. And Keras image transformer will actually take a Keras model object, and TF image transformer takes a TensorFlow graph object. So you can kind of use these at various levels of abstraction, if you will, depending on what frameworks you're using and so on. And internally in the implementation, these are just kind of calling each other, right? So you can imagine deep image predictor calls named image transformer with the model name, for example, in session v3. And then actually internally in there, we create a Keras model and then call Keras image transformer, which converts it into a tf.graph and calls tf image transformer. There's some reason for this. We'll talk about it in a bit. But this sort of hierarchy, we have it for images right now, but you can kind of imagine it for different domains like text and time series data so that you can work at different levels of abstraction. And for example, and these things will actually ultimately go to a transformer that takes arbitrary tensors or vectors. And we're working on a couple of these. So one thing that actually we've gotten some feedback from the community about is, can you support actual generic vector input models? And so that's in progress. And we also have a pull request for deep text featurizers, kind of like the image featurizer, but using things like word2vec. So I want to talk a little bit about the very bottom transformer, which is kind of the basis for everything. This transformer takes a tf.graph to define the computation, and it roughly does like 3 simple steps. One is when you call that transform, so you're applying this computation to the data frame, it's going to convert the image schema in this case into a vector, and then it actually calls tensor frames under it to efficiently distribute the graph itself to the workers and apply the graph on the partition data in an efficient way, and then returns the result as a vector. And we have the author of tensor frames here, so you can tell us a little more about how tensor frames does this efficiently. There you go.
Thank you. Yeah, so mostly, I hope that this whole hierarchy convinces you that essentially you can turn most of your deep learning transformers into essentially one that in Spark can ingest arbitrary kind of data and then output some other types of data as well. And so the question really is, how can we take data from Spark and just apply this big deep learning transform to produce some new data? So here we're using and here we're going to do that in the context of TensorFlow. So the question really is how can we do some high performance transformation using these neural networks? So if you look at most of the existing frameworks for doing deep learning, they have essentially 2 ways to ingest data. One of them is based on memory. So these frameworks usually have an interface in C or C++ on which you have some wrappers like Python. And these APIs, the C++ APIs, accept some buffers containing some data representation. So it contains your images or your vectors. These vectors are ingested by the system, by the runtime of the deep learning library, and then it outputs a new tensor or a new vector, a new matrix. So that's one of the APIs. The other API is usually file-based or transform-based. So in this case, for example, in the TensorFlow up to now, it has been based on this concept of queues. So in this case, you describe to the runtime of your deep learning system how to read some files. For example, you say scan this directory that contains all my images, and then build a classifier out of that. And so usually this directly ties into how you represent your data on files. So it's and then you hope that the runtime is able to efficiently fetch and pipeline all these operations to be able to maximize the throughput of the computations. So since we're working with Spark here, we tend not to look into the file system. The main reason being that Spark is really optimized for doing in-memory data transfers and data transforms. So that's why deep learning pipelines tries to minimize the number of the amount of time being spent on fetching data from disk. So in this context, Spark is responsible for producing the data. It uses all the Spark infrastructure for reading from CSV, from Parquet, and so on. And then this data is being transferred, and then is being passed to the in memory to the runtime of for doing deep learning, and then is used in the subsequent steps after that by Spark. So of course, there is a question of how you can integrate Spark and these deep learning libraries together in order to efficiently transfer data. So these low-level manipulations are handled in the case of deep learning pipelines by this library called TensorFrames, which can work at the level of tensors. So matrix, vectors, matrices, vectors, and higher dimensional representations. So I won't go too much into the detail into how it works, but you can think of every deep learning transform, so not training, but transform here, as, in the case of TensorFlow, as a graph of computations. And for example, here it has, it has two inputs, it produces an output. So you can map that in the context of Spark data frames by saying that each of the rows of a data frame is going to contain, if it contains an input X and an input Y, you can produce a new column of data by applying row by row these transformations. And there's a lot of details into how to do that efficiently, which we covered a little bit yesterday in the meetup, but that are detailed on the Deep Learning Pipelines website. But if you want to run batch inference, this is how you would do that using, so this is what happens behind the scene when you say transform on a data set containing images. So in that case, you start by expressing your computation from the Spark driver. And there you say, I'm going to, so in Python, you can say, I'm going to transform this data frame using this neural network. This gets translated, as Suan was mentioning, into a TensorFlow graph. So all this transform containing a neural network gets expressed as a big DAG of computation within TensorFlow runtime. And this graph then can be serialized and broadcast to all of the workers around in your cluster. And each of these workers will actually be the ones running TensorFlow inside, directly inside the Java virtual machine that hosts Spark. And then Spark will be able to take the data it already has in memory, or that it is fetching by itself, pass it to the TensorFlow runtime in this case, and then output the result of the transform. And the transformation, so you still need to do some data reshaping and manipulation to be able to go from one to the other. So I invite you to look at the TensorFrame website if you want to have more details for that. But this way we can guarantee some pretty good efficiency into running these models without having the user care about how the data is being laid out in memory or how it is being stored outside in a way that Spark would not necessarily understand. Because deep learning frameworks usually have a lot of ways to represent data. In this case, we bypass all the problem for the users while maintaining some good efficiency in the process. So let's so this was good for doing batch prediction, but of course, this is not the only way that we want to be able to use deep learning, and Sven will talk a bit about how to integrate with a SQL.
Okay. Yeah, the second promised way to essentially deploy your models in prediction was using Spark SQL. I think this is actually a really cool idea for really anything, not just deep learning. We just thought it was cool to say you can do deep learning in SQL. We put it in here. But essentially, the idea is you take a trained model or pipeline and register a SQL UDF so that it's really usable by anybody who can do SQL. Right? So the workflow is something like this. You can just call something like register Keras UDF. So this one will register Keras models. And you give it the name of the SQL function you want it to be, and then specify the Keras model file. And then in SQL, you can just call that function, which will apply the deep learning model to the data frame you're getting from underneath. So this is really powerful because now you don't have to be a deep learning expert or even know Scala or Python or anything. You could just be a BI, business analyst, and be able to call this on data to just kind of inspect and see what's going on in there. So I think this is a really cool way to deploy your models. That's underused, but we'll see. Right. It also means you can apply deep learning models in streaming, because Spark SQL functions you can call in structured streaming or other things if you can do this. We're almost done. Okay, like there's 3 minutes left. So I'm going to talk a little bit about what's going on now and the future. We kind of talked about some of these in-progress items, like Scala API for a deep image featurizer. So for that one, it makes sense to have a Scala API because there's 0 deep learning code actually involved from the user's perspective. And originally, when we released this, everything was Python because we were like, deep learning people are Python. But then I think that neglected the point of this library, which was saying that you don't need to be a deep learning person to do deep learning. Right? So we had a lot of kind of people in the community who were using Scala, and it was like, oh, I want to try this, but why isn't it in Scala? So that's one thing. Another thing we talked about was text featurization, which will do things like embedding from text, and the TensorFlow transformer for arbitrary vectors. And some of the future things we're looking at include distributed training. Matei this morning talked about TensorFlow and Spark and how that was integrating with the MLlib Pipelines API, which we collaborated with them on. We're trying to figure out how that might fit with this library or different solutions in general for doing distributed training with Spark. And maybe support for more backends, but we would love your feedback to see if there are missing things in there, use a different framework that you prefer, and so on. Please come talk to us. This is a very abstract slide. Anyway, so deep learning pipelines, simple APIs for deep learning with MLlib. Skills using Apache Spark for these transformers and estimators we talked about. Also the Spark SQL, which is really cool. And here's a deep learning, our GitHub site actually. Okay, I think we can take questions. I think there's 1 minute left, according to this. Yeah.
Awesome.
So I guess there's a microphone over there if you have questions.
So this is a more useful slide.
Yes, if you have questions, please queue up behind this microphone. We have time for maybe 1 or 2 questions. Just use this. Come up to this microphone.
Hi, thanks for the talk. I noticed that H2O was missing from the list of tools that's available for deep learning on Spark. It has a lot of different neural network architectures available, and it runs good as well. So I was wondering how you position yourself towards H2O.
Do they implement their own?
So I have a limited usage of H2O itself. My understanding that H2O has been working mostly on integrating very closely directly with the existing APIs of Spark. Also at a level that allows you to be probably more expressive in order to essentially to model directly your network. We have been trying essentially not to expose any of the underlying frameworks or any of the and trying to work at the high level of the API, because this library is really aiming at simplicity and allowing you to use Spark without having to necessarily know a lot about the underlying foundation that are being used here. So this is why it doesn't expose some of the parameters you would like to. You may be interested in using, for example, such as how you properly batch the data and everything. This is done for you here automatically. So there are also some other differences, and I'm happy to talk to you about that later.
Yeah, so unfortunately we don't have time for any more questions right now, but thank you so much for speaking, and you can find these guys around the conference next week.